Alrighty, folks. 6.34 was requested a bunch, so why don't we start with that one? 6.34. It's number 4 in the list. So I do what was asked for on the board. And then if we have time, I do more. Sorry. Now, guys, don't forget, we are recording. So, you know. Yes, Liam. Oh, cast it out to you guys? Yeah. Yep. And I'll even do it as a window so it doesn't completely stop what you're doing. All right. Good. 6.34. How much work is required for a 58-kilogram runner to accelerate from rest to a speed of 6.5 meters per second? So, if they're going from one speed up to another, what's changing about them? What type of energy is changing? Anybody?
They're accelerating.
They're accelerating, but what type of energy is changing?
Their kinetic energy?
Their kinetic energy, right, yeah. So, is it increasing or decreasing?
It's increasing, right? Because they're going from slow to fast.
Right, is increasing. Wow, that just fell apart quickly. I think I need to recalibrate here. Recalibrate.
Are you recording right now?
Sure. We'll share the calibration with everyone. All right. I might then follow up with this is done by work on the runner. So we know that work changes the amount of energy something has. So if the kinetic energy of the runner is increasing, then that's going to be accomplished by work being done on the runner. All right? Yes? Good. So we have on our equation sheet, I pull up our equation, here it is. We have an equation that says, oh look, the W net, the work net, the total work is the change in the kinetic energy. So that's actually where I'm going to start. But I'm also going to use the definition of work, which is force and parallel to the displacement. And I'm actually also going to use the definition of kinetic energy over here, where we have kinetic energy is 1/2 the inertia times the speed squared there. So I'm going to use both those and do a little thing. And what do they tell me? How much work is required to accelerate from rest to the speed of this? So we're going to look at the work. Actually, I don't need to use the work thing, so.
Work is not a vector, right?
Correct, it is a scalar. I actually don't need to use the definition of work because it just asked me the total work. Delta, let's see, is delta initial minus final or final minus initial? Or are they plus? Final minus initial. So one of those things that hopefully is seeping into your brain somewhere. What was the initial kinetic energy if it was at rest?
0.
So KE final minus 0. So we can kind of forget about that. And now I'm going to use that definition of kinetic energy, right? 1/2 mv squared, 1/2 mass of the runner, speed final of the runner squared. And now it's just a substitution game. Let's see. 58 kilograms, 6.5 meters per second. And given that I'm in base units of kilograms and meters and seconds, that's going to give me an answer out in joules. And so I should double check that they wanted an answer in joules, and they did. So, yay! I'm going to leave it up to you to multiply and square one number. Yeah, I think you can do it. It'll be good math practice.
Wait, which one did we just do? We did.
I don't know. I erased it. So we're doing when push comes to shove.
Was it?
It's on the video. It's 6 point something. 3, 4. Thanks, sir. Two forces of these magnitudes acting opposite direction on a block. So opposite surface shown in this figure. Initially block centered at a position. This sometimes later blocks move to the right. New position. Find the work 1 done by the block of a force magnitude. Find the work 2. Find the network. Determine the change in kinetic energy. Okay. Well, let's see. In our Y, this is push to shove, right? Push, shove. You would want to make sure, since it asks a lot about work, that you're clear about what work is, right? How do you perform work? What are the necessary components? And what must be true of those two? They must be parallel to each other. Good. So I would start off with something like work is performed or something. When a force is applied in the same direction as motion, and the object moves. Now, what's the difference between positive work and negative work? See, you would think direction, because we've always used positive and negative up to this point to mean direction, to mean right and left, up and down. With work, because it's a scalar, positive and negative mean increase the energy or decrease the energy. So if I do positive work on something, I'm increasing the amount of energy it has. So if I lift this pen up, is its energy increasing or decreasing as it goes up? Increasing. Its gravitational potential energy is increasing. So I did positive work on the pen. What about when I lower it down? Decreasing. So I did negative work on the pen. Not because it was up and down, but because I increased or decreased the amount of energy. I think we threw the ball around a little bit the other day, right? We said throwing the ball, I was doing positive work on the ball. You catching it was negative work on the ball because it decreased the amount of energy it had.
And then that also.
So that, huh? What? Which one? None. You'd be giving it kinetic energy, energy of motion. No, because you're not, by pulling it back, you're not working against the force, you're actually using a force to get it back. If you were using a mechanical arm and you stored energy like in a spring that then flung forward, that would be, but not, your muscles work off taking chemically stored energy, changing that into mechanical energy. So it's a more complicated movement than that. So in here, I'd also show negative versus positive work. to show that you understood that little conversation that we just had. That would need to be in your Y there. All right, so let's look. They want to know the work one done by the force one. So I'm going to say work, remember, is force parallel delta D parallel. So this is part A. And work one would equal force one delta D one. So in this case, mine moves from -6 to 5. So remember, delta D would also, I could write that as D final minus D initial, right? Anytime I have a delta. My force number one for me is 60 newtons. My final position, my DF, is for me is +5. I go from -5. I go, so that's 5 centimeters plus, whoops, sorry, not plus, minus a -6 centimeters. What do you mean, where's that? Yeah, that's my final position. So my delta D is my final position minus my initial position. Huh? Yeah. Yep. And then -6 is my beginning. So I've actually moved 11 centimeters, right? So, oh, wait a minute, that's centimeters. What do I want my units to be here? Probably joules, right? Yeah, in joules. So I better change that centimeters to meters. So 0.05 meters minus a -0.06 meters. So I get W1 is 60 newtons times no. Megan said she'd be back though. Yeah. I'm not sure if my boss is definitely back the other day. Okay. All right. And then this is, let's see, minus a negative is plus, so 0.11 meters. Right? And I'm going to get a positive number. Good for part A? All right, let's go on to part B then. Yes, just with the odds before. Now notice what this force and this displacement are in opposite directions. So is this force going to, the first force, did it add work or take away work? Or add energy or take away energy? Added energy. So we got a positive. We should have gotten a positive answer. What about this one? It's going to take away. So I want to make sure, even though I'm going to get a positive answer again, I want to make sure I put it in as a negative. Yeah. Remember, that's the part I put in parentheses when we talked about it. Said yeah. So the other way to say it, you could do this, you say, well, I want to remind myself, so I'm going to put in a negative value for the force to give me a negative work. Doesn't really work that way, but you could think of it that way to make your life easier. So for B, I'm same formula, W2. My force for W2 is 50 newtons. Again, I have 0.11 meters. It moves. So I find W2, and I'm going to make this negative, and then it would be in joules. Whoops, I've got the joules here. But I basically do the exact same thing. Then pot C. Part C and D. In part C, the net work. Oh, that's the total work, right? How many forces do I have on this block doing work? 2. Now, we know that there's a weight of the block and a normal force, right? But there's no work because we're not moving in that direction. So only these 2 do work. So how am I going to find the total work? Add them together, which is going to end up being a subtraction, right? Because one's negative. So take your answer for A and add it to your answer to B, and you get your answer to C. So we'll write that up. Part C, W1 plus W2 equals W net. And then part D, in D, they want to know what's the change in kinetic energy, right? Oh, I had an equation last time. See, I had the W net equals the change in kinetic energy. So it's my answer for part. Yeah, that's what they wanted you to realize is that work net and kinetic energy formula there, which we already knew because the one we did. Okay, so 6.57. They want to know the power fly walking straight up a window pane. Let's see, power is the rate that you do work, right? So is the fly going to do work going up the window pane? Yes. And this is where we kind of make a decision about which way we want to look at it. We can either look at it as, well, the fly's doing work going up the window pane, therefore there's a force and a distance, right? What force does the fly have to oppose to go up the window pane? Gravity. So we can say, okay, and what's the other name for the force of gravity on something? That's synonym. The weight of it. So we could look at the weight of the fly and how far it moved and say that's how much work was done. The other way to think about it is what does that work do? What type of energy does it give the fly? Potential, because it's moving up. So we could say, well, the fly gains potential energy from this work. So we could look at how much potential energy it gains. Well, let's say this. Because they don't tell us about it. Let's say the fly is moving at 28 centimeters a second when it starts, and is moving that fast when we get to the end of the time we're looking at it. Has its kinetic energy changed? No. So yes, it has kinetic energy, but it hasn't changed. All of the work the fly has done going up the pane has gone into creating more gravitational potential energy. So we can either look at that work directly or look at how much the potential energy of the fly has changed. Which way do you guys want to do it? Okay. We can also, wait a minute, they're maintaining this speed. We don't even need to look at that. We do need to look at the work. We need to look at the fact that.
Does it give us the distance that they go or no?
No, what it gives us 6.57 is it tells us that the fly must use a force equal to its weight to move constantly up the pane.
Doesn't have to be bigger than its weight?
No, that would mean it would accelerate.
Oh.
Because here's our happy little fly, right? It has its weight down, and whatever force it applies, it pushes off the window with up. And how much acceleration would that have? None.
But it can still be bigger.
Right. The acceleration is how its motions change it. Power is related to the speed the fly travels, since the faster it travels, the higher rate it must work. To kind of bring that down to an idea, you know, if it's traveling every centimeter it travels, it has to do a set amount of work. The faster it travels those centimeters, the faster it has to do that work. And power is the rate that it does that work. That's why we look at power, it's work per time. And if I break that out, work is force delta D, right? Yes, no? Okay. Little rearrangement. What's delta D over delta T? What's the rate that the displacement changes? The end of the V. Velocity. So this is force times velocity. And that's actually, or force times speed, that's actually on our equation sheet. If you look on our equation sheet, power is power here, and force times speed here. So, back in the land of our problem, the force is going to have to be equal to the fly's weight, and then the window, and then times his speed. But his weight is in grams, the speed is in centimeters per second. Now, one thing, they ask for the answer in milliwatts. If you want to just do it in watts, you can erase that little m. It'll allow you to do that. So you can do it in watts rather than having to convert to milliwatts. But what I'm going to have to do is I need to take, what was it, 1.5 grams? Yeah. I need to take 1.5 grams, and that is 0.0015 kilograms. And I need to take my 2.8 centimeters per second, and that's 0.028 meters per second. Because I want to work in my base unit, so I don't have to worry about that I get out some weird multiple of watts. And then I'm going to put those in, so my force is going to be the object that fly's weight, right? And probably be a good idea. Oh, you do all those problems at the bottom, that's weight, right? The weight is M, the mass, times the gravitational field strength. That's those 6 problems for practice on the bottom of the assignment. And I know I'm hurrying here to get this done before the block. So I'm taking my mass, multiplying it by 9.81 newtons per kilogram. That's the weight. That's the force that he has to use. I'm going to move all that down. I want to write this as one big thing. There we go. Times my speed, which is 0.028 meters per second. That's going to give me the power in watts. So make sure that take away the little m. Or you could take your answer and multiply it by 1,000, and then it'd be in milliwatts. So let's see. See what I get. Can you, while I do this, can you go up and do the exit ticket, please? But and I get a really small number. So I'm going to get rid of the milli. And I'm going to put in, see, it wants 2 sig figs. So I'm only going to put in 4.1. That's 2. The 2 doesn't cause the one to round up. Use my times 10. And in here put in -4.